Before we move on to the big theorem called the Buckner theorem, basically characterize all the functions, all the positive definite functions on your locally compact abelian groups, I just want to give some motivation and also giving now some examples. So first of all, let's do the following proposition. So one way of constructing positive things is take something with the convolute with this involution. So what you can do is that if you take a function inside the CC of G, and you can consider f convolute with the involution of f, okay? So this one, well, of course, CC of G, you can treat it as in the L1 function, and you get something in L1, but another way of saying this is that you can think about CC of G as in L infinity, and when you convolute two continuous things, you have something that's also continuous, so you can treat it as inside the CC of G, which is inside the L infinity of G now, okay? So this is going to be a function defined from G to C, and it's going to be bounded. This one is in fact positive definite, okay? So the proof is quite simple. So if you have any C1 up to Cn inside C, and any x1 up to xn inside G, you want to show the double summation is going to be non-negative. So you do the double summation over all the ij going from 1 to n, ci cj bar of your phi evaluate at xi xj inverse. All right, so phi by definition is the convolution of these two functions, so you write it as an integral. So you have this double summation ci cj bar. Of the integral now, we have first function is f, evaluate at xi xj inverse, and then you take, say, y, and then you do the f check, evaluate at y inverse, okay, dy, okay? So things are abelian, so this formula does work, okay? Don't need to worry about the modular function. Let's just replace the f check of y inverse as the f of, you remove the inverse basically, and you remove the check, and but you need to do the conjugate, okay? So they're the same. All right, so now this is kind of a standard trick I've seen several times. So now you can just translate your y because you have a left invariant integral, okay? So which one you translate doesn't really matter. You can do the you can do the I or the J. So here, let's just do the J. So you do the y translate by xj on the left, okay? Because things are technically abelian, so it doesn't really matter you do it on the left or right, okay? But in any case, you remove the xj inverse in the first f, okay? This becomes xi y. But the second y, now you multiply a xj on the left, okay? So f of xj y, okay? So that becomes that integral. And you can move the double summation inside the integral. Everything is finite here. And what you realize is you're basically integrating some positive thing, okay? So what you're integrating is the norm of the summation of ci f of xi y, okay? You take the entire thing norm, and your double summation just disappears, okay? So you take this double summation times its conjugate is exactly what you're integrating. And because you're integrating something that's non-negative, in the end you get something non-negative. So your function, this phi, is indeed positive definite. Well, this way, if you just replace this f by inside not only in CC of G, you can actually replace by in L2 of G, the same formula basically still hold. You can't really do it for L1 functions because this phi, if you do it this way, you may not get something that's in L infinity, okay? So things doesn't really work that way. But in any case, if it's in CC of G, you do have something that's positive definite function constructed in this way. Well, now we want to kind of characterize all the positive definite function and to give a kind of a motivation why the Buckner theorem is what it is. Let me show you the next two lemmas. So first of all, well, if you consider a function, let's say phi inside the dual group, well, being in the dual group is a function defined from G to the complex number, okay? And you know it's not only in the complex, but actually goes to the unit circle. So you know this phi is indeed bounded, so it's in L infinity. Well, this one is actually going to be positive definite, okay? So every character is always positive definite. Well, the proof is kind of trivial. So for every x1 up to xn inside the G, well, because you have a character, so everything is multiplicative. So if you think about what happens when you have xi inverse xj, well, then this is phi of xi inverse times the phi of xj. And another way of writing it is the phi of xi bar phi of xj. So if you think about what happens to your matrix of these xi inverse xj, well, this is essentially just well, this n by n matrix, you can break it as a n by 1 times a 1 by n, where you put phi of x1 bar up to phi of xn bar first. And then on the row matrix, you put phi of x1 up to phi of xn, okay? So when you multiply these two matrices, well, you get the matrix, this n by n matrix. And this one, when you multiply a matrix by its conjugate or a vector by its conjugate, is always positive definite. Basic linear algebra, so this is positive definite. Okay, so let's finish the proof that every character is going to be positive definite. And as an immediate corollary, well, if you think about if you have two characters, you add them up, okay, or not only characters, if you have two positive definite functions and you add them up, well, then they clearly, again, is positive definite, okay? So it's close under addition, and it's close under scalar multiple of some positive scalar. And what are some other ways of combining these characters? Well, if you think about your character as in the dual group, okay, there are elements on your dual group. And if you take a measure, your dual group is a locally compact abelian group, so it has a measure space, let's say M of G hat, okay? If you take any measure where this measure mu is greater than or equal to 0, okay? Well, now this measure, basically you can integrate respect to this measure, okay? So if you consider kind of mixing all your dual space, this dual group, these characters by this measure mu, then you can get a function, let's call it big phi of mu, okay? So let's use the notation big phi of mu for now. So if I want to evaluate x, I just integrate all the phi of x, the mu of phi. Okay, mu is a measure on the dual group on the characters. Okay, so basically I'm fixing x and I integrate across all these characters. Okay, this one is going to be positive. Okay, you can think about this as kind of a linear combination of these positive characters, a positive combination of these characters. So this one is going to be positive definite. Okay. I'm not going to prove this fact. This is just essentially follows immediately from the previous lemma, okay? But the idea is this is one standard way of constructing a positive definite function on your group. And in fact, we just want to show the converse is also true, okay? That's going to be the main theorem called the Buckner theorem, okay? So let me maybe just state the theorem here. So here is the theorem we're going to prove in the next video. So this is called the Buckner's theorem. All right, so it's essentially the converse of this corollary. So for every phi that's positive definite functions on a group, well, that's actually, it's positive definite if and only if I can find a mu inside M of G hat, so that this phi is equals to this this formula phi of mu. Okay, so in other words, all the phi x is given by an integral of these characters. Okay, so d mu of phi. Okay, so this is kind of the idea or the motivation behind the Buckner theorem.